Welcome to Beyond the Qubit. I'm your host, Frank Dekker. Today's guest is Jonathon Riddell. Jonathon is building developer tools for quantum science. He's building a platform that lets researchers express many-body quantum models. Jonathon is also for many years active on YouTube, and there he's teaching quantum many-body physics problems. So with that, thank you, Jonathon, for being here, being a part of the show.
It's my pleasure.
First of all, could you give us a short introduction?
My background is I hold a PhD in quantum many-body physics. It sounds like we're going to dive into what that means today. And like for the listeners at home, what that means is that I'm very quantum computing could be thought of as like a subdiscipline of this community. And so it's a much broader, sort of up in the clouds view of problem sets in that space. And so my PhD is from McMaster University and the Perimeter Institute. Shortly, 3 years after my PhD, I started Kothar Computing. So I'm the founder and CEO of a new scientific computing startup that's really aimed at unlocking the looming age of quantum computing.
Okay, cool. What created your interest in quantum technology?
So, when I came into research in my bachelor's degree, it was really like it was kind of like a match made in heaven. My favorite courses were quantum physics the first time I took it. The second one was thermodynamics, and then the moment I took both of those classes, I went to my quantum physics professor and said, "How do I mix these two things?" And he pointed to me towards a new hire at the time at the university I was attending who was mixing both of those things, and then I got really deep into modern quantum many-body physics research. And so while I was doing that, I also I'm a very pedagogical person. I think a lot of resources are much more complicated than they need to be, whether that's getting involved in computing for science or whether that's learning advanced topics in a variety of contexts. So I started my YouTube channel. I had YouTube going and my own PhD research going at the same time. And I was making videos that were adjacent to the quantum computing community. And so at the time, I was more or less ignorant to the quantum computing industry. This was 2018, 2019, very the height of the NISQ era, the height of the variational quantum eigensolver era. Is this going to be useful? And I made a video about the Jordan-Wigner transformation, and an investor reached out to me and was like, "Hey, do you want to come consult with us because we want to form an investment thesis around quantum technology?" And at the time, it was very difficult to separate the hype from the real science. And so I a little bit out of my comfort zone started reviewing companies, technology proposals, and kind of really assessing where the technology space was while I was in the middle of my PhD. And this kind of opened my eyes. The research that I do is that I did, I'm no longer doing research. The research that I did is very broad. The tools and the descriptions that we work with fit into the space of quantum computing. They fit into the space of material science. They fit into the space of quantum chemistry. It's the natural language of quantum computing. I'm just describing qubit systems and what they're doing in a variety of contexts. So this drove me towards quantum technology and being really interested in what the community was doing. And this has been a long rant, but I'll just punch it off with one last thing, and that is that it was very clear then, and it's still very clear today, that the future is a hybrid quantum classical computing. The writing was on the wall almost a decade ago when we were doing this research, and it's becoming more and more clear. So that's one of the key things that Kothar plugs there, is really having a deep and robust thesis on what hybrid computing looks like in the future.
Let's park it for a moment and we come back to it. First of all, I want to know, how did you become the CEO of Kothar?
Kothar, yeah. So how did I become the CEO of Kothar? So when I finished my PhD, I went off to do a postdoc, and in between, there's a very specific pain point that I was thinking about, in conjunction with my consulting. So along with quantum many-body physics, I'm an expert in high-performance computing to simulate these systems. And in some sense, these systems and this type of simulation, it's very hard, and it's one of the primary reasons why you want to build quantum computers. It's to simulate systems of many quantum particles, so you can simulate things like molecules or or materials. And so when I came into my PhD, the type of physics that I wanted to simulate, there was really no packages to write anything. And if you wanted good performance, if you wanted to push the boundaries of a physical simulation, you needed to get down basically at the computer science level, write C++ code, learn, parallel computing frameworks and all of this stuff. So I spent my PhD writing probably 100,000 lines of code, like 5 years between my master's and my PhD. I then jumped across the Atlantic, across the pond, and I spent 2.5 years in Nottingham and Birmingham working on, I kid you not, like an adjacent field. Like the questions that we were asking were identical, but the code that I had written in my PhD was just not applicable. Like there was a couple pieces that I could use. So my first project took me 30,000 lines of code to write, and so while I'm thinking about uh, while I'm thinking about what's the future of computing, it's hybrid computing, the classical workhorse, the engine's not really there. And then I'm also thinking that you're either making a choice like me, where you're basically becoming a computer scientist, a high performance computing developer to do your science, or you're not making that choice and you don't have good access to computational tools right now. Like that's the state of the quantum community. So I started toying around in my spare time with a sort of building out a universal engine for these
And
types of.
Jonathan, why is that? Why are there no good tools available? So it is ridiculous that if you want to do to solve those problems, that you have to become a full-time programmer.
It is, but this is the accepted status quo. So if you want to do circuit emulation, companies like IBM, Intel, basically every quantum computing company has built really good tools for you to emulate what a quantum computer is doing. If you're in other niche areas, specific quantum material contexts and stuff like that, maybe someone in your community has built a semi-okay library that is like pretty efficient. But the vast majority of time, physicists, when we pull the community, most physicists get like one class in computation in their undergraduate degree, and then they're thrown into modern research. And modern research is not, some people are just doing math, some people are doing experiments, but a lot of modern research is just doing computation. And so you're asking people to learn on the fly whatever they need to learn at the time, basically. So this is the status quo, basically. So like the finding that perfect match of someone that has the right computational background and has the right physics backgrounds to write these libraries, those people are really rare.
Yes, I can
And
imagine.
not every community has people dedicated to that space.
And to your point, if it would be easier, the pool of developers or the pool of researchers who could solve those problems would be much wider because the
It
barriers
would
to
be
entry would be
this.
much lower.
Yeah, exactly. And like the type of the speed of innovation, the speed of R&D would also go up significantly, right? Like this is what happened to the machine learning community. A lot of the core libraries, PyTorch, TensorFlow, they're all written in C++, high performance computing code. They have GPU acceleration, backends, etc. But the vast majority of AI and machine learning developers, they don't code at that level. They code at an abstracted level inside Python. So you need tools that are designed from the ground up for your community, and then your community can innovate on top of them.
Can you explain what you want to achieve in the coming 5 years?
In the next 5 years, like our core goal right now is really unlocking what's called quantum electronic design automation, and tools surrounding like that context. So that is the sort of like the enterprise grade. What's our highest impact on the quantum community today, and that's giving them. It's kind of interesting, right? Like while we're trying to build quantum computers, is I don't know if this is where you want me to go with this, but basically there's a fundamental classical computing bottleneck that you need to solve, that Kothar solves, to help scientists, focus on just scientists and engineers just focus on building quantum computers rather than trying to write in-house simulations that allow them to see if what they're building is going to be optimal. So that's the big application goal. The other big goal is to become the de facto provider of scientific computing tools in the quantum, like in all quantum spaces. So that's you sort of like deep R&D research, like deep research in academia that doesn't have immediate applications, but that's also folks writing hybrid quantum classical computing algorithms on the platform, as well.
That's clear. Thank you. What are the main battles that you have to win to achieve your goals? The two goals.
That's a good question. I mean, there's technical battles, there's business battles. Like I think a really interesting thing about the quantum space is that it's such a green space. Like it's not a we don't have quantum computers yet at a utility scale that are solving real problems for research or industry. So one of the fundamental business challenges is figuring out how to integrate and monetize what you have and what type of monetization models are available and optimal for the growing community. Like this is a really interesting one. On the technology side, like what we're trying to solve is we're trying to give hardware providers the ability to basically effectively model, like, let's say 100 qubits. For example, the quantum dot or spin qubit context, that's beyond what they currently can build. In the superconducting qubit case, in other contexts, this is lower than what they can currently build, but it's beyond what they can currently simulate. So really, like capturing that physics at a high enough resolution is a hard computational job, but we feel like we have the right roadmap to achieve that in the next year or two.
Okay. And how are you going to do that?
That's a good question. So there's like two layers to quantum media that we really slide into. One is solving high resolution simulations of individual qubits, like really getting down to the dirty details of the quantum mechanics that's going on in those contexts. So just to preface this, we have a partnership basically with a company called Nano Academic. They build a product called QTCAD. And what they're able to do is they're able to build us realistic models of what's going on the chip. And so there's two layers to where we slide in. The first is modeling individual qubits, or maybe high resolution of like very small amount of qubits, but containing a lot of quantum information. And this is more or less, this is like a really, not to be super technical, but this is a very messy problem, because you basically have a lot of different things talking to a lot of different things. There's not a lot of structure to the problem, but with our tools, mixing symbolic computing with high performance, we're called exact diagonalization routines, we're basically able to, as far as I can tell, get the hardware providers to where they want to be already. When you zoom out and you look at the chip more from like an effective compact model perspective, then you're talking about advanced tensor network routines. But basically our solution is delivered through QTCAD or our partners software. So it's a full stack development. It takes you from the fundamental physics layer all the way up to the effective model of your chip. And you can basically construct from basic information about the thing that you want to build and on what material, realistic models of your chip, all the way up to the effective physics of your chip, fully capturing the quantumness of that chip.
Okay, let's park the technology a little bit. We come back to it. First,
Sure.
I want to get to know you a little bit better, Jonathan. What are your fundamental beliefs that shaped you as a personality and your character?
Yeah, I think I think just going back to the beginning, I think the fundamental driver, why I'm so drawn, why I was drawn to make my YouTube channel, why I was drawn to making Kothar, is that I fundamentally believe things can be a lot easier than they are. Basically, it's easy to get. It's possible to build tools or courses or material for people to get involved in advanced topics much faster than we are getting them involved in those topics, and it's possible to make those things very accessible for people. So this is the fundamental driver for me.
That sounds like solving a very big pain point. So that should be value add already. That sounds
Yeah.
exciting. But can you then maybe, that's your fundamental, but do you have other examples of key beliefs? So one key belief is making it simpler and easier to access, and that you create value with that. And you've been practicing that for many years also with your YouTube channel. But what other key fundamental beliefs do you have that could help you running Kothar Computing?
Like I'm also like a fundamental believer in things like division of labor and specialization and collaboration. So there's lots of content, like it's like you might want to ask the question, for example, who should be running the simulations and who should be building the simulations for for quantum chip manufacturers. And to me, the natural answer to that is not the chip manufacturers, because they're hiring for expertise, a specific set of expertise to construct the hardware. They don't internally, typically, unless they have a lot of resources, have the resources to build a software stack that actually helps those folks. And then when you then go and also look at the software stack that these people should be importing to do that, you also have like different layers of it, right? So like there's a pre-existing EDA community. It's the reason why the classical chip community is as successful as it is. And so there's a lot of institutional knowledge going into, how could we actually model these chips, right? And it's just, basically we're going to succeed as a community if we collaborate and we build layers that talk to each other too, right? Like software orchestration is also a major bottleneck, making things speak to each other. So it's collaboration, it's integration, it's division of labor, and finding your niche and how you can help the community. And that goes all the way down to how we construct the team at Kothar. What type of division of labor we have, what type of generalists we hire, what type of specialists we hire.
What are can you give 3 lessons that you learned during your career or during your youth that really shaped your personality and your character?
Yeah, I think that's an interesting question. I would say one of the lessons that I would find is that I would say is that leadership comes in all shapes and forms. In principle, though, for engineers and researchers, the best type of leadership is something that approximates a flat structure with very obvious leadership coming from areas that people can respect and understand and can justify itself. Hopefully that's clear, but it's basically like, for example, in Kothar, to give you an example, the way we structure the team is it's more or less a flat structure. However, people have specific areas that they own. A lead high performance computing developer, if something's a matter of speed, he's the person that is like fundamentally in control of that conversation. And I think that's the big takeaway for at least running a company of our size. You can really unleash people onto problems if they have the time and space and ownership over the problems that they're developing on. I think Kothar's progress is quite remarkable for how young of a company we are and how ambitious of a scope that we're tackling with the amount of employees that we have. So that's definitely a big one. A second lesson is, I guess where would I want to take this? Like there's lots of lessons to be learned. Like I think like a big one is just to be uncomfortable and forcing yourself into situations. Like there's been many moments in Kothar's journey where it's like, is it I come from an academic background. One of the first things that I did that was uncomfortable was putting my face on a screen and putting myself out there on YouTube and just pushing through that, right? Because like the outcome and what you want from that experience is more important than the anxiety in those contexts. Like a lot of the anxiety that you have to not put yourself out there and push through the pain, it's not really real, right? And like in Kothar, it's the same thing. Like when we wanted to construct a list of beta users, or we want to get out in front of a specific company, it's like it's okay to be shameless and just private message people on LinkedIn, because that's what that platform is for, right? Like that's what it's for, and so it's okay just to start those conversations. Yeah, I would say those are the 2 big ones.
Okay, thank you. Could you walk us a little bit through how did your extensive movies on YouTube, how did it help you in your network, building your network and your knowledge levels? Or were there totally different learnings, or are there obvious things that you say, okay, this is how it benefited me?
So the network is a really interesting one because I get recognized all the time. Like it's a niche channel. It's built for a niche community in physics. It has about 7,500 followers. And there's very famous physicists that have many more citations than I have. And it's very rare for a physicist to walk up to you and ask you for a selfie. It's only happened to me once, but like that's kind of like every conference I go to, people say, "Hey, you're Jonathan. I've seen your YouTube." It's happened in the context of venture capital firms that are interested in quantum. They hire physicists to do their due diligence, and those physicists have often, like, they know who They know who I am. It also helps because like before I meet people, a lot of people Google me and then they see that I'm a nice guy and they come in with expectations for, a friendly conversation. And then, as I mentioned at the beginning, I mean, this is how we found our initial investors. We built that relationship over years of me consulting for them, and then they were the first money to come into Kothar to start building out like building out the solution to the problem that I wanted to solve.
So summarizing is starting the YouTube channel that really helped you to get recognized and building a brand. And it also
Yes.
brought venture capital on your path and helped you
Yes.
raising capital.
Yes. Yes. Absolutely. Yeah.
That's quite cool.
Yeah.
Okay. Jonathan, could you walk us through where do you get energy from?
Yeah, I'm one of those people that likes the little things, likes the little victories. So back in my research days, it was like when the plot comes out the way that you want, it's like a huge energy boost. You get really excited about it. Fun conversations about new projects really get really get me excited. And then I'm just I'm a very like results and a results driven person. So, if I'm not making progress, it's I'm not someone to lean on my accomplishment for the last year. It's really like what have you done for me lately, and it's getting to the next goal. It's continuing to drive to the things that I want to do continuously. That's basically where I get energy from. It's continuously the satisfaction of hitting goals is basically what keeps me going.
And where do you decide not to give energy on, not to spend time on?
That's a good question. That's a very topical question too, because like when you become a CEO, it becomes a moment of budgeting your time a little bit. And so the very cheap and uninteresting answer is that I focus on whatever Kothar needs that week. And that's where my energy goes. The more interesting answer is, I'm very motivated by, you know, um, yeah, a very vague answer, but things that I find deeply interesting. And if I don't find something interesting, I'm not super motivated to interact with it. My friends call me like a specialist. If you talk to me about quantum physics, if you talk to me about building a startup, or if you talk to me about, I'm fascinated by a very very particular part of history, the middle Republican era of Rome. If you're not talking to me about that, then I'm not super excited. So I'm a very specialized person. I drive full head into the things that I'm excited about, and I kind of have blinders to the rest of life.
It sounds very similar to me.
Yeah.
In some areas I have interest, I like to know a lot, but other very obvious areas I know almost nothing about.
Yes.
Jonathan, maybe let's dive a little bit into Kothar Computing. How would you describe Kothar Computing to people who don't know it in very basic terms?
Yeah. So Kothar is building developer tools for scientists and engineers to solve cutting edge problems in quantum technology in the quantum technology space. So that's building it's essentially trying to build the Google workspace from data generation to publication or patent for cutting edge topics in quantum science and technology.
And why did you focus on research and on academic research specifically?
So I wouldn't say that we were focused on academic research in particular. I would say that we started the company wondering what our first application space would actually be. When we were thinking about the early, who's our customer, who's the person that we want to use these tools, there's a very large community of material scientists and condensed matter physicists. Basically people responsible for all the cutting edge innovations in electronics, materials, like all of those spaces. And Kothar was really it's a passion project that's really motivated by the pain I felt as being a part of that community. And then the question that we had in the early days was it's not really a question of will this be industrially relevant. It is what community will we choose first to help, and who has the most pressing need for tools like this. And so there's a lot of context where people want to develop hybrid algorithms for a variety of contexts, molecular simulation for drug discovery, tons of questions in material science. But the quantum computers aren't really there. The fun, like, I guess the entry point and the best place for our tools to start being useful was the quantum EDA space. Yeah, I guess the summary is not specifically focused on researchers, but to us, they're kind of the fundamental building blocks. This is where a lot of innovation comes out of. This is where the new technologies come out of. This is where new algorithms will come out of for quantum computing. And so they're kind of a foundational tool that, or like not a tool, but a foundational community that drives towards industrial applications.
Okay, that's clear. Can you walk us through a little bit where do you sit in the value chain? For example, I also interviewed the classic computing.
Yes.
And also QC design. How do you differ? So there's many companies trying to set up software. It is a big bottleneck, software. But could you explain a little bit on how do you compare with competitors, or where do you differentiate, and what is different and what is similar? And maybe are they above you in the software stack or below you? Or
I would say that the goal of Classic, for example, like if you zoom out and what we're both trying to do, it seems very similar to the point where I would say we're at the same part. We're at the same part of the software stack. The core difference is like we're basically both trying to get quantum computing in front of people, and we're trying to get good computational methods in front of people. Classic comes at the problem from a fundamentally different perspective than Kothar. And that perspective I would basically define as them being quantum first, and us being scientific computing first. So my goal isn't to make a platform for people to do quantum computing. My goal is to give everyone a platform to do computing efforts that may or may not include quantum computers. A space where everything is designed from the ground up to basically host an ecosystem like that in a way where scientists can just be scientists and they don't have to worry. I mean, you have to worry about if your algorithm's running on a quantum computer or a classical computer, of course, right? But like leaving it at that kind of abstraction layer where they're thinking about it like this. This is what the quantum computer is good at. This is what my GPU is good at. This is what my CPU is good at. And making it very easy for them to program in that perspective. So I would say Classic is much more of a pure quantum play. And from my perspective, the community, they're also building in an ecosystem that wasn't designed for quantum computing. It wasn't designed even for quantum physics simulation on the classical side. It was designed as kind of being a front end for C and Fortran libraries. It's been co-opted and very much adopted by the machine learning and AI ecosystem. And so Kothar also has a fundamental thesis that Python is the wrong ecosystem for quantum computing. We need new programming tools fundamentally that are designed from the ground up for our community and the type of programming paradigm that we're in. And this comes from years of experience interacting with a variety of different levels of programmers, right? Like you can meet physicists that are basically computer scientists, and they'll go into like the C++ standard and what people were talking about in 2023 and why this new feature is going to change everything for development. And then you'll find users, people that are developing, and those are people that are good at implementation. And then you'll find completely opposite people, and they're the people developing the frontier of algorithms. And how should we actually push classical computing forward? And they can barely program. Those are this is the range of community that we have to support in our ecosystem. And I think it's just time our fundamental thesis is that we should bring programming for science and specifically for physics into 2025. A lot of the community is building based off of technology that was founded in the 90s. We can do a lot better than what I think the current outlook is from our peers.
So maybe to summarize, is you have both the same goal, making programming for quantum simpler. However,
yes.
Kothar wants to focus not only on quantum, but on the total physics. And Classic is more based on machine learning tools. That was their existence. And what you say is you want to build it from the ground, bottom up, from the ground, really tailor-made for physics computing.
Yes, and just like the one clarification is that Classic is building into the Python ecosystem, which is an ecosystem really propped up by the machine learning community. So that was the point that I was trying to make there.
And why is that not the best platform? So what are the disadvantages if you go that path?
Yeah, so if you're a computer scientist,
can you
yeah.
contrast it with what are the disadvantages versus what are the benefits? That would be very helpful.
Yes, absolutely. So the advantages of Python is that it has a fantastic and very large ecosystem. I would say, and right now they also have the added benefit. So there's a company called Modular AI, and Modular AI is building Mojo, which is a superset of Python, and they're solving a lot of the performance issues of Python, but they're not fixing Python itself. Python kind of exists in like a corner in Mojo, and Mojo is this much bigger thing. And like that's just kind of the way it is. So I would say if you're a computer scientist or you're someone that's very deep into high performance computing and you want to use all of the cutting edge things that are coming out of Python, you're very comfortable making that your life, like integrating Python packages and really understanding underneath the hood what's going on. I think you can create an ecosystem like in Python that works. Pure Python can't be compiled. It just has, and compiling is the fundamental bottleneck between making something fast and something being very slow in modern programming languages. And so the community in the AI and machine learning space is doing all kinds, and the HPC space is doing all kinds of things to get around how slow Python is. And
is it really slow?
The problem,
I wasn't aware of that.
It's incredibly slow. Like you shouldn't be writing. If you want to do anything that has any type of performance, you should not be writing native Python code. You should be calling into libraries that were written in C++, C, or Fortran. And so that's what Python's strength is. It is the front end of these libraries in some sense. You do lose a lot of like translation between modern plus and Python. And then Python itself, like you can't, the problem with Python is that you can't take what you built in C++ and then do complicated things with it that you didn't anticipate at the C++ layer to create new things in Python. Like that's not something that you should really be doing. And so Aleph basically adopts a very similar, which is our tool, our programming language. It's designed to be, which is slightly different from Python. Python is designed to be kind of a front end for C. Aleph is designed to be a front end for C++. So it's designed to take full advantage of what the HPC community is doing, but it's faster than Python and it's designed to be compiled itself. So it's as easy to write as Python. It doesn't have the downsides. It doesn't have the speed downsides of Python. There's also, it's very difficult to write safe Python code. Like I don't want to get into technical details.
Yeah, I like it. I think also for the listeners it's good. One of the benefits of a podcast is that you can always replay. We are investors are not the smartest people. So especially on technical, we don't have a PhD of quantum technology. At least some have, but not all of us. And then it's really very helpful for the technical details if you can do replays. But I think the devil is in the detail. So we do want to know so if you can explain the detail, yes, please.
Yeah, so I would say like one of the maybe the easiest thing to understand about the issues with Python is that there's no strong typing. And what that means is that if I declare a variable x and I set it equal to an integer, I can just change its type. And this is I can change it into a real number, or I could change it into a string, or I can change it into whatever I really want. And this makes compatibility with compilers in particular. Like the way Python is designed is it will never be a compiled language. And then the extra difficulty is because there's so many people in there, people are saying, okay, well, what if I write like a domain specific language? Maybe I write something that's like a subset of Python, like Numba, for example, and I compile code with Numba. And the question that I ask myself is like, do I want my developer to be an expert in physics, or do I want my developer to spend 6 months of their PhD trying to figure out how to optimize Python code that you would never have to optimize in the same way in another ecosystem if it was developed for them. So we call this internally, and other folks talk about it's kind of like the software orchestration. The Python ecosystem is so vast and so complex. There's 3 to 5 libraries for every single little thing that you want to do, and sometimes they're not compatible. different meshes and spider webs of libraries are compatible with each other. And why are we asking physicists at the cutting edge of science to make decisions about this? That doesn't really make sense to me, right? If I'm trying to build a quantum computer, why am I worried about if my NumPy package is compatible with some other package in the version numbers are off and I don't know why my Python code isn't running? Like that's just it's a silly state of scientific computing software. And so Aleph backs away from that. From the orchestration problem, the goal there is much wider. It is to say, like Python has all those orchestration problems just from the software perspective. Then if I'm developing on my laptop and then I plop it up on a supercomputing cluster, they might not have the packages that I installed, or their version numbers might be different, and the behavior might be slightly different, or the performance might be slightly different. And at that level, you're also asking scientists to figure out how to coordinate files between potentially different supercomputing clusters, their local resources. You're asking them to figure out SSH. You're asking them to figure out scheduling and distributing, requesting resources on scientific computing clusters. And Kothar's answer is, this is silly. Like, we talk to other people that are worried about the orchestration problem, and their solution is to try and make something that collects all of the mess and pushes it together, and they try to make it their mess rather than someone else's mess, right? But Kothar's answer is, why don't we just step aside and say, let's take all the good pieces. Let's build something that's as easy to use as what people are already attracted to, and build it from the ground up with the modern compute landscape. In the language solves the ease of use problem. It solves the performance problem. It also integrates with C++, which is where all of the momentum from the HPC community is coming from. It's in C++, so it's designed to take advantage of that. And then on top of that, you slap it into a platform called the Workshop that handles, hook our app into your different computers. We kind of sit on your computer like we're the Dropbox app in the bottom right hand corner, and then wherever you log on, you can submit jobs to the compute resources you have access to. If you need to install drivers for your GPU, we handle that for you. It's completely removing the need to worry about all of the things that like plague modern scientific computing research and completely derail research with software problems.
Okay, thank you. Let's zoom out a little bit and let it sink in.
Absolutely.
But what I also want to know, I want to go a little bit into the basics of the technology. First, some terminology. Can you explain in basic terms what are many-body quantum models?
Yeah. So I'll do it through like basically like layers of technologies, right? So as we push technology to be smaller, I would say that the type of physics that we use to design semiconductors and your GPUs, your modern electronics, this is what I would call semi-classical physics, or maybe easier would be to say not strongly correlated quantum systems. Still small, there's still some effects that you need to take into account for, but not really. Quantum many-body physics is the layer of physics that you get to when you want to design electronics and technologies taking advantage of pure quantum effects. So a quantum computer is a quantum many-body system at the end of the day. What you're trying to do is you're trying to engineer a system that is basically a programmable quantum many-body system. So all of the qubits, every time you connect them and you want to entangle them, they're two quantum bodies, and then they're interacting. If I have 1,000,000 qubits in my system, that's a quantum many-body system. And so when you think about, for example, I'm building some novel electronic, I need to understand how these 4, 5, 10, 20 electrons all interact with each other. Depending on the type of physics that's at play, it's either I can ignore the fact that they're talking to each other, or I have to take into account that they're talking to each other. And if I have to take it into account, that's a quantum many-body system.
Okay. And why is it important to look at the whole system versus looking at the individual parts?
You have to do both, but the fundamental advantages in quantum technology come from things like entanglement, superposition. It's fundamentally the quantumness of the devices that we want to exploit here. And in that context, you have to look at how they communicate with each other, basically. Like quantum advantage. I mean, there's lots of buzzwords like quantum magic and things like this, but a very easy way to think about it is that you need, there's special types of entanglement where this isn't true, but you need entanglement, broadly speaking, to have quantum advantage and actually build utility scale quantum computers that can solve real problems. And like that at that scale, like that is the quantum bodies talking to each other. It's not just the individual components, it's everything combined. Like the quantum systems, you have to consider a quantum system in its entirety to understand its behavior. That's the special part about quantum physics over classical physics.
What did you learn from your research in many-body quantum physics?
Like in terms of what I applied to Kothar.
Yes.
I would say that there is a lot of structure that we're not taking advantage of when we simulate these systems. A lot of problems, a lot of problems basically boil down to finding the correct shortcut to be able to make them computable or more computable than they currently are. So basically, it is that structure matters and structure needs to be exploited. And then quantum systems are like, we talked to a lot of other startups, and I think the thing that I envy about other startups and their story is that a lot of times they're building one thing that solves one problem. If you want to build a universal simulator for quantum many-body systems, I mean, first of all, you have to support multiple compute paradigms. You have to support quantum computing, you have to support classical computing, and you have to support when they both talk to each other and do that. That's a separate problem. But if you're just looking at the classical ecosystem of simulation methods, you're also talking about having a solution space or like an algorithm space that is incredibly large. Every problem can't be treated. There's no one, like the quantum computer is the one trick solves all quantum many-body problems. The classical thing though is that there are hundreds of directions that you can go, and the true power of classical computing is found when you can combine different methods in different contexts to push yourself past specific barriers, and that's basically been a theme throughout my research career. So I've written, I've written quantum Monte Carlo, I've written tensor network algorithms, I've written a lot of exact diagonalization algorithms, type binding algorithms. These might not mean anything to you, but basically there's so much that goes in and so much structure that can be exploited that the tools, this is another reason, back to one of your first questions, is why don't better tools exist? And it's just that to actually come up with a design where all of these tools in different directions can talk to each other, work with each other in a way that doesn't cause significant overhead is like on its own a significant design challenge and kind of a huge success of Kothar's.
Okay. Yeah, let's park it a little bit for customer adoption and initial. Now let's just dive into it. What are the initial feedback that you get from your customers? If you do proof of concept studies with them, what is the traction and the feedback that you get?
Yeah, so I guess just a status so we can know where we are, just to like set the stage, is that we have one industrial partnership. We're talking to folks. We're in early conversations with a number of other folks about maybe adopting our technology. And then we also have 100 academic beta users. The very positive stuff is people are surprised at how fast it is, and people are surprised at how easy it is to get started. Once they get started, I would say like one of the things that we're trying to build right now is that our onboarding process was not good. So like one of the key things that I would think is at the top of VCs' minds when they talk to us is like, how hard is it to get really technical folks that don't like programming to adopt a new tool? And the answer is that it needs to be very obvious that there's a benefit. So if I can show you a tutorial that does significantly better than what you can do on your own with the current tools that you're using, the transfer is easy. People adopt the tool. If I go talk to them and we're missing a feature, they're not going to move until we have feature coverage. So this is like the good is people are like when it is working for people, they're surprised at it's how good it is. We're like, if you're writing pure Python code, there's a really good chance we're 10,000 times faster than what you're writing. And so something that might take you a week is now like a couple seconds, maybe a minute. And like that would be like the top end of what you would do for your project. And now that is kind of the starting point of your project, and you can push beyond that and ask more ambitious questions. So people are really excited about the speed. Adoption is the core bottleneck that we're solving by more feature coverage, better learning materials, getting this in front of more people, that kind of thing.
Okay, interesting. Can you walk us through the barriers of entry for competition? Yourself, you're still in an early phase with proof of concept and beta testers. But let's dream big. You will succeed in 5 years' time. What are the barriers to entry for others who want to copy Kothar?
That's an interesting question, and I would almost go and I would talk about what people are doing today, because it's not like people aren't trying to solve the problem that we're solving in terms of creating the classical part of hybrid computing, or at least that's a subset of what we're doing. And I would say one of the large barriers of entry is getting the right talent concentration with the right specializations in the same room. Like, a question that you might ask yourself is, do I hire 1 physicist and 9 computer scientists, or do I hire 1 computer scientist and 9 physicists? And the answer really depends on what type of physicists you have access to. And so we're really lucky to exist in an ecosystem and in an area where it's easy to find high quality numerical physicists. Now, that's kind of like the talent aspect of the barrier of entry. Like, an NVIDIA is always going to have money to hire talent, and they exist in an ecosystem with a lot of talent. And then in 5 years' time, like, what we're going to see is that, like, if Kothar's vision, which I strongly believe it is the right vision, then they have that vision in front of them, right? Like, NVIDIA has never been scared of basically copy and pasting someone else's vision and just hooking that up to an NVIDIA GPU with their computer scientists being able to, like, unlock that. So the next thing is like, there's a lot of infrastructure in Kothar and a lot of algorithm development that is novel, that it's not easy to see at face value when you're interacting with our systems. So there is a fair amount of, like there is a tech lead from that perspective, algorithm perspective, approaches to the computing. A big thing for us is symbolic plus numerical computing with an overhead. That's not easy to copy, but, like, at the end of the day, software is all about velocity and stickiness. And so, like, that will become our moat long term.
And how do you create it?
How do you create it?
I think the velocity and the stickiness. Let's take them separate.
Yeah. Let's take them separate. But I think they're coupled, though, right? It is the stickiness, and the, like, you get stickiness by continually driving in the direction that your users want you and need you to drive in, and you get velocity by ensuring that you're not taking unnecessary detours. Like, something that you see with a lot of other younger founders and things like this is detours away from the main goal. And sometimes you have to remind your people on your team, sometimes it's like, yeah, like, this, what you're doing is cool, but you just wasted a day of our development time. So it's being really results and goal oriented while maintaining not just velocity but the correct velocity too. It's basically maintaining the right amount of quality as you push hard towards well-defined goals that are given to you by user feedback and what the community cares about. So, for example, something that we're talking internally right now is that we're supporting spin qubit quantum computers, and we're driving towards superconducting qubit quantum computers. And so a question that you might ask is, like, do you stick just with those 2 platforms, or do you eventually start developing tools for other platforms? Like, what about neutral atoms? What about these other modalities that people are building stuff on? And the answer is that you continue to expand both. You go deeper into one, and then you continue to build partnerships with the other community. Like, people look to leave if they have a reason to leave, and it's about continuously, like, being very diligent. Like, speaking to folks at, like, AWS, Amazon, it's about being customer obsessed and really caring about what your customer wants and needs. And for a tool like ours, we need to continuously innovate and not fall asleep at the wheel. Sorry, I'm ranting, but I want to give you one more example. Like, that is, like, a user came in our beta, and it was basically like, hey, I have 2 choices right now. In terms of symbolic computing, I can either go and turn my life, the next 4 years of my life, into Mathematica, or I can go turn the next 4 years of my life into Aleph. Now, here's my problem. You have features for magnetic systems that I want to use, but I don't want to use them for magnetic systems. I want to use them for fermion systems. And it's like, yeah, feature coverage is an issue, and continuously having those conversations to make sure coverage is there for the types of problems, the new problems that need to be solved, not the old problems.
Okay, thank you for clarifying.